We have 11 o'clock now. I mean Moscow time, anytime it's Moscow time for me. And the first speaker, Oleg Morzhin, with the talk on optimization of coherent and not coherent controls in some significant system. Это моя интерпретация, но неважно, значит, каждый прочитает, как он хочет. So, s'il vous plaît, Oleg.
Good day. I'm glad to give this talk. Thanks a lot to Ivan Remezov, to his colleagues, to Sergey, and this the first day of the spring, and I'm very glad this day is very sunny, and I'm glad to give this talk, this large talk, to open the. I'm glad to open this session, and my talk is about optimization of controls in quantum systems. Of course, you know about this important actual direction in modern science, modern mathematics, and I want to say to another possible participations, maybe students who don't know some introductory words. Firstly, from variational calculus, optimal control, some time ago, this important direction was analyzed more intensively, and I want to say that the first works about optimal control in quantum systems were, for example, in 1980s years, for example, Vadim Krotov, Budkovsky, Samolenko, and so on. And nowadays, this direction is more popular. A lot of papers in various journals around the world, and it's a pleasure to give this talk according to the Semigroup conference. And I want to say that optimal control theory optimizations methods are used here. This work combines different results from physics, quantum mechanics, from mathematics, optimal control theory, and so on. And speaking about numerical solving optimal control problems, I mean mathematical problems, mathematical modeling for quantum control, and according to the mathematical theory of optimal control, we consider optimal control problems for quantum systems, for quantum mechanical equations with controls. In ordinary classical physics, of course, we have quantum mechanical equations without controls. And in this direction, such equations are considered with various controls. For example, coherent control in the Hamiltonian, in the Schrödinger equation, some perturbation in addition to the free Hamiltonian, and so on. And if we speak about numerical solving for such optimal control problems, I want to say about some methods used in this domain. Firstly, I want to say that some part of such methods are adapted from the optimal control theory beyond quantum control. For example, the conditional gradient methods, the projecting gradient method, and so on, are well known in the optimal control theory. For example, from the book by Demyanov, Rubinov, from the article by Levitin, Oleg, and so on. And the second type of methods is such methods which are derived especially for quantum systems, not such adaptation. I mean constructing especially for quantum needs. Further, I will talk about so-called two-stage methods suggested by Alexander Nikolaevich Pechin, and these methods was proposed by him especially for quantum control problem, and it's not adaptation of some well-known methods from optimal control theory. And speaking about numerical methods, I want to divide them to these two parts. Infinite dimensional optimization. For example, steepest descent method, conjugate gradient method, conditional gradient method, gradient projection method. I mean that we have some functional derivative gradient of our objective functional, some functional. Further, Van Dragen maximum principle, Krotov method, Vadim Fyodorich Krotov, well-known scientist. He worked many years in Institute of Control Sciences, Russian Academy of Sciences, Jurabit's method, also Madej-Turinich method, and so on. Further, the second group, various parameterization of controls and finite dimensional optimization. For example, GRAPE, gradient ascent pulse engineering, compare with this steepest descent or ascent method. This method uses piecewise constant parameterization for controls, and such parameterization gives reduction to finite dimensional optimization, where some special formulas are used. Further, shopped random basis crab method, for example, Tomasi Kalarka and others. Various order optimization tools, including, for example, genetic algorithms, differential evolution, dual annealing methods, also node-Mead method can be used also, and so on. Further, I want to say about the following two important aspects. When we solve optimal control problems, we consider some objective functional, and it's very important to say about possible low upper estimations. For example, if we want to minimize Gilbert-Schmidt distance between the final density matrix and some given target density matrix, of course, you want to obtain zero value for this distance. But maybe for some conditions, there is such the global minimum of this objective functional, which is larger than 0. Or maybe some another functional which should be minimized or maximized. It's very important to estimate our objective functional. And it can be used, it can be possible to use, for example, finite dimensional optimization over complex manifolds. For example, see this paper. For example, when we consider Gilbert-Schmidt scalar product overlap between two matrices, we consider, as I said above, our finite state rho in the finite time t large. But when we consider simply rho matrix instead of the final state, instead of final state, we consider now some function at the set of our density matrices and some manifold, and we can obtain, for example, upper estimator, which is used in our computations. For example, this estimate, it's very interesting. The second aspect, which is mentioned here, is studying effectiveness of various methods. For example, local methods, different gradient methods, global methods, for example, stochastic methods such as annealing methods, and so on. It's very important to estimate effectiveness of various methods used in our computations. Of course, for effective solving and analyzing of quantum control problems. Further, in this talk, we consider 1 and 2 qubit quantum systems, open systems, only open systems we consider just now, and we consider Goriny-Kosakovsky-Sudarshan-Limbunt master equation, and we see this part, effective Hamiltonian, dissipative part, some parameter epsilon positive, free Hamiltonian, some perturbation with coherent control. This effective Hamiltonian depending on incoherent control due to the LM shift, and this dissipative part, because the system is considered under its environment and possible interactions with some reservoir of various intensity can be used here as a resource. It's interesting to consider the system's environment as a resource. Not consider only such obstacle. It's interesting to consider as a resource to to understand how to use the system environment, and we consider that's why we consider incoherent control. In addition to coherent control is some ordinary situation in a lot of papers, and coherent control is studied by us, and I want to pay attention to these fundamental papers, and this required a constraint to incoherent control according to the physical meaning, and the dimension we consider an order density matrix, and n is equal to 2 4 when we consider correspondingly 1 and 2 qubits, and we in various our papers we consider various also various objective functional constraints, classes of controls, various goals for investigations, mathematical, physical goals, and further I want to say about the two-stage method. I said above about this method. This method is from this paper. This paper is devoted to the problem for the open system of such type, and it's very important problem was considered. I mean, controllability problem, approximate controllability problem for open systems at the set of density matrices, and this paper gives very interesting, important results. Among them, this two-stage method was given, and this method was constructed for not only for approximate solving the steering problem. Steering problem, I mean that it's needed to generate such final density matrix rho of t that coincides in the meaning of Gilbert-Schmidt distance, coincide with some given rho target density matrix. And this method was proposed according to the problem of for analyzing approximate controllability. And here we consider this method the meaning for solving our steering problem. This method contains of two stages. I mean that the time stage is divided to two parts, for incoherent stage and coherent stage. At the first stage, we consider only incoherent control under zero coherent control, and at the second stage, coherent control is used under zero incoherent control according to this method. And the goal of the first stage is to obtain such intermediate final density matrix which is sufficiently close to the intermediate target density matrix, which is constructed by us by the following way. This matrix is diagonal, and its eigenvalues are given in the descent order, and these eigenvalues are the same with our matrix rho target. And the second state should make such rotation and that move via coherent control to our target with some appropriate precision. And I want to say about one qubit problem here. For example, this paper, and some other papers. Our papers consider this system, this case, 2 by 2 density matrix, and this superoperator of dissipation is used here, and our controls, coherent and incoherent controls, are scaled here, and due to the block parameterization, this formula, we reduce our system to this form, bilinear system with real valued states. It's more appropriate for classical control theory, of course, and for computer realization. And we consider also 2-qubit system. The density matrix is 4 by 4 matrix, and here we consider this interaction Hamiltonian, and this matrix is considered in these two variants. And this paper, this consider the 2-qubit system. The superoperator of dissipation has this form. Omitting the details I talk because the time is constrained, and I want to say that this parameterization can be used here for reducing our quantum system to this bilinear form, bilinear system. Further, for the two level system, 1-qubit system, we consider, for example, this statement is needed to solve the string problem, and also this problem can be considered with free final time, which should be minimized. And the paper, this paper, which will published during this year, this paper considers various results, and among them we have the results for this problem. And we consider the first stage of the two-stage method, and this particular result is the following. It was derived. We derived the exact representations for intermediate final states at the end of the first stage, and exact representation, explicit exact representation for the objective function. It's derivatives. It's very important. I mean that the objective function depends on the vector of parameters, because we consider here piecewise constant parameterization for incoherent control. That's why we have reduction to finite dimensional optimization and the corresponding objective function. And this function is written in such a form that we have explicit formula for depending on the control parameters. And omitting the details, I want to say that this exact formulas for the objective functions gradient, it's very important result. And here we use the projecting version of the heavy ball method. This method is very popular. From this paper, the projecting version can be found in this paper also for finite dimensional optimization. Yeah, and for our problem, we use this projection method, and we consider the following example. Set this initial density matrix and the target density matrix is such the following. In the terms of the block ball, we have this point and this point, initial and target points. In other words, it's needed to move from the block sphere to the point inside the block ball. And according to the unmodified two-stage method, we sort the engine value is in descending order. And after that, we consider this intermediate density matrix, this point in the block ball, and constant incoherent control according to the unmodified method. And the modification of the method is obtained when we consider piecewise constant control and optimization of control of such type. This approach gives the corresponding modification of the two-stage method. And this picture is interesting. We see that we starting from this point on lying on the block sphere. We go to this point. This point is target with minus, but this plus not minus, because intermediate target point in the block ball. And the first stage is ended when we reach this point. And it's interesting that from this this point, from this time, we see that our incoherent control and these functions, I mean x1, x2 are 0, and coherent control is considered to be 0 according to the method. And these 0 functions are computed automatically according to optimization. And physically, this observation means that we have the situation when we use the system resources for moving along this axis. Further, it's needed to move from this intermediate point to this target point. And the second stage considers this class of coherent controls, and we optimize this control, and we have this trajectory in the ball. Control of this type when we have zero values at the start and at the final time. Smooth switching on and off here. Further, consider the two-qubit system, and the problem of maximizing this Gilbert-Schmidt scalar product, this overlap, and this parameterization according to the formula which was shown here. And in the various our papers, we consider this system. And this slide, of course, my talk cannot cover a lot of results, of course. And this slide is devoted, for example, this slide is devoted for to satisfying zero controls. All our controls are zero here, and these controls are such that the Pontryagin maximum principle is satisfied here. It's a very interesting situation, which means that it's needed to use any control, coherent or incoherent. In other words, the system is able to realize achieving the goal. Here, according to some conditions, it's very interesting to find such conditions, of course. Some particular goal of our research. And here, if we consider some another control, some initial guess, and if we want to show that various methods converge to zero controls with various precision according to the L2 norm. We can use, for example, the two-step gradient projection method. I mean, the projection version of the heavy ball method. But in contrast to my my consideration, which was above for the finite dimensional problem, here we consider such the method in infinite dimensional space of controls here. The gradient of our objective function now is used. We consider the minimization problem here, and this value is the upper bound for the overlap. It's the largest value for any error target, and the upper bound when we consider these sorting conditions. And we see here that we obtain such the diagonal functions that at the time stage realize achieving the goal. And we see that our overlap, this blue solid line becomes very close to 1, to the upper bound at the final time. And other characteristics, for example, this entropy and so on. Further, the next important aspect which should be mentioned now is deriving various interesting methods for our quantum problems according to the known similar methods known in the optimal control theory beyond quantum control. For example, if we read this wonderful book written by Vadim Fedорович Krotov, we see in particular the method which can be more effective in comparison to some another method, some gradient method, some situation. Its situations, this method is very interesting. And in quantum control, the various adaptations of the Krotov method, of the general Krotov method, are very popular. I don't give in these slides a large list of such references, but there is our survey in the journal Russian Service, Mathematical Service, I mean Успехи математических наук, our paper written by together with Alexander Nikolaevich Pechin. Our survey, this survey was written and published in this journal some years ago, and completely devoted to the Krotov methods, Krotov types methods for various quantum problems, and our survey covers a lot of papers by a lot of scientists around the world and for closed systems. That's why I don't give more references here. And also I want to say about this interesting book, Beyond Quantum Control. And this book contains, among other important results, such the methods which can be considered as some adaptation of the general Krotov methods for some particular optimal control problems. And my next and these slides are also about some particular adaptation of the general Krotov method and for quantum control. Firstly, there is a question about the importance of such adaptation, because when we consider quantum system, so quantum optimal control problems, we have the corresponding specifics. For example, it's clear that we have density matrix, some complex matrices, some another situation in contrast to ordinary consideration with real valued states in the classical optimal control theory, classical Krotov method. And we have some another important aspects. For example, if the problem is linear with respect to control, so it's a very interesting aspect because if we consider such a statement is some very important. It gives some important reason for constraining our controls because similar to the corresponding consideration of the Pantragi maximum principle, here we also should to maximize some function and it's needed to constrain our controls and so on. A lot of various aspects can be found when we consider quantum statements. That's why it's very important to work for adaptation of various methods known in optimal control theory, in finite dimensional optimization theory, for effective and rigorous, it's very important to note, a rigorous consideration for quantum systems. And that's why I want to say about the adaptation, the general Krotov method for the problem of maximizing the Gilbert-Schmidt overlap. We consider for unification, we consider the statement when we use some illusory functional, which should be minimized, and according to the general approach, we consider the corresponding adaptation of the method, and it's very important to note to this increment non-standard increment formulas. Such formulas can be used, can be found by you in this book by Vladimir Andreevich Sorochka, Beyond Quantum Control. In contrast to the classical increment formulas, I mean classical when we consider free shade and derivative gradient of some objective functional, this objective functional. Here we have not any residual. These formulas are both. These formulas are exact, and these formulas have not any residual. It's very important in comparing with the ordinary approach, gradient approach, also second order approach. The classical these approaches use only the first or two first terms. I mean variations, and when we consider various objective functionals, and it's very important to obtain such the formulas for this control problem for another statements. When we can obtain such the exact increment formulas without any residual, because we can use this potential of the increment more effectively. For example, this book by Vladimir Andreevich Sorochka contains such situations when the similar methods can improve non-optimal single control. I mean control which satisfy to the Pontryagin maximum principle, and of course, any gradient method cannot improve such controls. And this book gives such the situations when non-optimal controls are improved. And this method use such as a exact increment, non-standard exact increment formulas. And it's that's why, in particular, that's why we work for adapting this approach for our quantum consideration. But this system is which such the right-hand side, which in general is discontinuous with respect to our state variable. But if we use regularization for our objective function, now we obtain smoothing and the corresponding system which is, contains some another mapping, not this mapping, such the system are continuous with respect to rho. This system is also with right-hand side, which is discontinuous in general, discontinuous with respect to his state co-state variable, and also regularization give the similar system with continuous with respect to his right-hand side. And various four methods we have here. Four because we have two this increment formulas exact, and with or without regularization. And this paper submitted to some journal contains very interesting, the corresponding very interesting results, the details for deriving these four methods and the corresponding analytical numerical results. And for in particular, we compare the regularized rho method, this method, I mean, this message written is this non-explicit iteration formula, and this method is compared with the one-step gradient projection method considered in the infinite dimension optimization. This important difference between the methods. Here we use our Fréchet derivative of gradient, and here we use only our background given from the previous iteration for us. And the next approximation is constructed according to this formula using this background information from our previous iteration. But now we have the co-state function computed from the adjoint system, and this new trajectory is derived, should be derived together with a new control, this vector control, according to solving this such as the similar system. I mean, the similar because we have regularization, not exactly this system, of course, because the system without regularization is considered. But the idea is the same, that it should should realize this non-explicit message. And these comparative results are given here for some conditions. We see that the regularized He method is faster here, and the methods depend on the parameter alpha projecting or regularization parameter, and different meanings can be considered this parameter. And this table shows that it's very important to construct adapter to adapt various iterative methods for various quantum optimal control problems, and consider such the methods rigorously with theoretical, numerical details. And also I want to say some another objective function, some minutes, 1-2 minutes, some another illustration today. It's needed to generate such the density matrix rho of T, some final, such as the final density matrix, which coincides with a given rho target, and to minimize our final time. And this is the next objective has the following meaning. It's needed to obtain such the Gilbert-Schmidt overlap which coincides with some given value. Of course, if this stirring is possible, of course, maybe there are such the conditions when we cannot reach this value m large or this matrix, of course, with the needed precision. And here we consider such the class of continuous controls, coherent and incoherent controls. We have here scalar coherent control and two-dimensional incoherent vector control. And due to this parameterization, we have reduction to finite dimensional optimization. And here we use the dual annealing method, some version of the general annealing approach for stochastic global search for finite dimensional problems. Such methods don't use gradient of an objective function, and realize some strategies for global search. Of course, because of the stochastic nature of such methods, just of the dual annealing method used here, it's very important to make more than one trials runs of this method and compare the results, select the best result, of course. And we have here the following results. The distance is the final result is rather close to 0. Comparing to this value, this plot shows the subsequence with monotonically decreasing distances. These values are given from the history of the dual annealing method working in some of several trials. And here we use, we see that the distance decreases to 0, starting from the 0 time, the point that the time 2 is close to 0, to going to this final time. This final time is computed automatically according to this objective functional, where some penalty is used. And at the conclusion, I want to say that here we consider some number of important aspects for 1 and 2 qubit quantum open systems. We consider various objective functional, various constraints, classes for our controls, various directions for adapting known methods for quantum systems, and for optimizing and controlling quantum systems, and in particular, very interesting, important growth type methods mentioned shortly, and so on. Thank you very much for your attention. Maybe some questions for me. Thank you very much.
Oleg, thank you very much for the talk. Any questions? We have about 2 minutes for questions, 2-3 minutes. Okay, then thank you very much again. And so we are ready for the next speaker.